makes the entropy, this is near zero, this is near zero, this is finite, so the left side is near zero. And therefore, the right side is near zero. So in case Fanel's inequality is this, and the text we have it in various levels of generality. One of the levels of generality is sharper than Fanel's inequality, and the lowest level of generality is simpler. It replaces the h by a 1, which is an upper bound on the entropy of a binary random variable that's error or not error, and so on. So the application that I alluded to before is the following. If I have some index in the set 2 to the n r, what do I mean? That's an integer 1, 2, 3, up through 2 to the n r. And I turn it into a sequence of inputs for a channel, and it goes through this channel and comes out with some random output drawn according to the conditional distribution of y given x, and then turn that into an estimate w hat, an integer estimate of what w is. Then it would, what I would say in this case is 1 plus probability of error times log of the number of values the input takes on. In this case, the input's w, not x. That's log of 2 to the nr, that's nr, greater than the entropy of xn given yn. So it puts a lower bound on the probability of error given the conditional entropy. Okay. So this leads to statements of the converse for Shannon's second coding theorem, where Shannon's theorem says if your rate of communication is less than capacity, you can make the probability of error go to 0. And a converse would say if the rate of the communication across the channel is greater than channel capacity, then the probability of error blows up. In particular, it goes to 1. But Fanel's inequality is a little too weak to show that it goes to 1. It's just bounded away from 0. So that's the application. Okay, let's prove it. Proof. We don't have to use anything else. We can just use the calculus of information that we've been developing. Let E be the random variable that is equal to 1 if x hat not equal to x and is 0 if x hat equals x. So it's the indicator random variable for whether or not you make an error. And the setup was you have x goes to y goes to x hat. All right. Then let's expand h of e and x given x hat in two different ways. So this is the error random variable, and this is the x that we're trying to guess, and x hat is the guess. So they're all related random variables. So I'll write it this way. First, the entropy of x given x hat plus the entropy of the error given x and x hat. Now, leave some space if you're taking notes. This is also equal to the entropy of error given x hat plus the entropy of x given error and x hat. This is one of the quantities we want to handle. What's the entropy of the error given x and x hat? Well, if I know x and x hat, I know whether or not I made an error. I just see, are they equal or not? So the conditional distribution of E is degenerate, given x and x hat. So this is 0. That conditional entropy is 0. Now, this is E is a binary random variable. In any case, let's throw away the conditioning. This is less than or equal to the entropy of E. And that, of course, is H of the probability of error. So this is less than the entropy of the probability of error. What about this term? Well, this is less than or equal to the probability of error given log of the alphabet size. Why? I'm going to write this as a probability that E equals 0 times H of x given E equals 0 and x hat. Well, if E equals 0, then I haven't made an error, and thus, if I haven't made an error and I know x hat, I now know x. So the conditional distribution of x given that E equals 0 and knowledge of x hat is 0. plus the probability that E is not 0, that is, that E is 1, that's this, times the entropy of X, given E equals 1 in X hat. But the entropy of X given something is less than the entropy of X. And the entropy of X is always less than log of the alphabet size, as we showed last time. So this is log of the alphabet size. Actually, a slightly sharper version is, I could say, log of the alphabet size minus 1. Why? Well, if I didn't make an error, and I know X hat, well, I know one of the values that X doesn't take on. It doesn't take on that value X hat. So the remaining alphabet size is just log X is X minus 1. But those are trivial improvements which are not needed, especially when we look at the asymptotics. All right. Now when we're all done, we have this quantity is bounded above by this plus this. In short, we have exactly h of x given x hat bounded above by this Fanow's inequality. And by Markovity, we can show this, but let's look at that, what we mean by Markovity and sufficient statistics, so on. But this is a weaker version. And when should we just look at the side information rather than the guess based on it? Weaker or stronger? All right. That's not right. You know, when I write down an inequality, I reserve the right to be correct within a flip of the inequality. Now, wait a minute. That's not a trivial remark. At least with the right sense of the inequality, it's always true. Now, there's something I want to skip over. Well, let's say I just want you to review, show that, just review a log sum inequality from the text and convexity of dpq in P and Q. I won't lecture on that. It's in the chapter 2. It's not directly relevant to anything we'll be saying for a few lectures. Now, let's look at the question of Markovity. When we're done with this discussion, this particular part will become evident. We say x, y, z is Markov in that order.